Okay, let's start looking at the end of this chapter when we're looking at colligative properties. As I said before, these depend on the number of solute particles, not on what those particles are. And these colligative properties all revolve around the idea of vapor pressure. And here's the deal. The vapor pressure of a solvent over a solution is lower than the vapor pressure of the pure solvent. What that means is if we had a jar here and we had this as a pure solvent in here, then you have a certain number of those particles up, or these solvent molecules up in the vapor. If this was pure water, there would be a certain vapor pressure of water. There would be a certain number of water molecules in the gas phase above the liquid water. However, if you put in a solute, and now the water has a solute in it, what you'll find is there are fewer water molecules in the vapor phase. Adding a non-volatile, meaning not going to evaporate very well, high boiling point, non-volatile solute to water lowers the vapor pressure of the water molecules above there, lowers the number of water molecules in the gas phase above the liquid water. All right, let's say it again. The vapor pressure of a solvent over a solution is lower than the vapor pressure of the pure solvent. And this can be looked at mathematically with Raoults law. The vapor pressure of the solvent is equal to the mole fraction of that solvent times the vapor pressure of the pure solvent. Let's look at it backwards. If you see the vapor pressure of the solvent, if it was pure solvent, this would be its vapor pressure. Multiply that by the mole fraction of the solvent, and you get the new vapor pressure of the solvent, which will be lower than the original vapor pressure of the pure solvent. Note that Raoult's law is in general for ideal solutions where you've got a low concentration of your solute. The concentration of your solute is fairly low, and that's what we tend to see. All right, so this can be derived. It's not the most difficult derivation, but I don't care about it, so about you being able to derive it, so we won't worry about it. But here's the deal. Because when you add a non-volatile solute, the solvent to a solvent, it lowers the solvent's vapor pressure. So that could be a change in the pressure, and it only lowers it a little bit. But the change in the vapor pressure of the solvent, we can say that's the pressure of the solvent, new pressure of the solvent minus the original pressure. You know, any change in anything is final minus initial. So the change in the pressure, the vapor pressure of solvent, is the final vapor pressure, which will be lowered, minus our initial vapor pressure. And through some math we won't go into here, this Raoult's law can be looked at as the change in the vapor pressure of the solvent equals the negative mole fraction of the solute times the original vapor pressure of the solvent. All right. Meaning the change in vapor pressure is proportional to the mole fraction of the solute. Note, let's not be confused. Raoult's law is the vapor pressure of the solvent equals the mole fraction of the solvent times the original vapor pressure of the solvent. This equation here is just a derivation where we're going to look at the mole fraction of the solute. And so the change in vapor pressure of the solvent is the negative mole fraction of the solute times the original vapor pressure of the solvent. All right. Let's do an example here. Let's look at one of these types of problems. So here we have this deal. Say you have 0.2 moles of a non-volatile solute, and you put that into benzene, 100 grams. So you have 100 grams of the liquid benzene. You dissolve in 0.2 moles of a non-volatile solute. Question, what is the vapor pressure at 60 degrees Celsius? All right. Well, a few things. What's going to be the mole fraction of the benzene? If we're going to use Raoults law, we want the new vapor pressure. So let's use Raoults law, where the pressure of the solvent equals the mole fraction of the solvent times the original vapor pressure of the solvent. The mole fraction of benzene, well, let's see. We've got 100 grams of benzene divided by 78.12 grams per mole, means we've got 1.28 moles of benzene. This is just grams divided by molar mass equals moles. That gives us moles of benzene. So that tells us we have 0.128 moles of benzene, and we added 0.2 moles of our non-volatile solvent. So the mole fraction of benzene is the moles of benzene divided by the total number of moles, or 0.128 plus a 0.2, and we get 0.865. That is the mole fraction of benzene. Well, note when we're dealing with Raoults law, let's write that again, we know that the pressure of the solvent is going to equal the mole fraction of the solvent times the normal vapor pressure of the solvent if there's no solute in there. And so what have we calculated so far? Well, we've got the mole fraction of our solute benzene. So this 0.865 is a mole fraction of benzene. The question is, what is the normal vapor pressure of benzene at 60 degrees? Well, that's something you're going to have to look up in a table or on an exam. That number will probably be given to you. Turns out that 60 degrees Celsius, the normal vapor pressure of benzene is 400 millimeters of mercury. Again, that is a number that would either be given to you or something you look at a table. So now we have our mole fraction of benzene. Now we have the normal pressure of pure benzene at 60 degrees Celsius. So Raoults law tells us we can just plug them in. Mole fraction times the normal pressure. Our new vapor pressure of benzene will be 346 millimeters of mercury. Cool. And where these numbers can become useful and interesting is in the colligative property of the first one we'll look at is boiling point elevation. Okay, it turns out that when you add a non-volatile solute to a solvent, the boiling point of the solvent goes up. If you have water boiling on the stove, if you add a non-volatile solute to it, the boiling point of the water goes up. It boils at a higher temperature. And that deals with vapor pressure. So let's look at this. Recall from previous chapters, the boiling point of any liquid is the temperature at which the vapor pressure equals the outside pressure. Recall, if you've got a pot of water and it is boiling, here's some water. It is boiling means all these gas bubbles are rising from the heat on the bottom to the surface. But if this is water in here, what's in this gas bubble? What is inside this bubble? Well, that's just water vapor. This is just a bubble of water vapor gas. Note, if the outside pressure, if the pressure of our atmosphere is greater than the pressure inside that bubble can't form. You can only get a bubble here, you can only form gaseous bubbles of water if the pressure inside that bubble is greater than the pressure of the liquid surrounding it, and the pressure of this liquid surrounding the bubble is atmospheric pressure. All right, so the boiling point of water is 100 degrees Celsius at 1 atmosphere of pressure, 760 millimeters of mercury. Okay, so that's something we're going to assume that we're in 1 atmosphere of pressure. We're going to assume we have 760 millimeters of mercury of pressure. All right. Note, if we looked at a table, again, this number has to come out of the table, the boiling point of benzene, if you just Googled that, what's a boiling point of benzene, it'll give you 80, I believe 80.1 degrees Celsius is the boiling point of benzene. And note that's assuming at 760 millimeters of mercury, normal atmospheric pressure. Pure benzene boils at 80 degrees. What we're saying then is you have to increase the temperature of pure benzene to 80 degrees Celsius. And once you've increased the temperature of benzene to 80 degrees Celsius, then bubbles will start forming, because at 80 degrees Celsius, the pressure inside a bubble of benzene is going to equal 760 millimeters of mercury, so that bubble can form. All right, but the question then is, what if we looked at our solution from up here? What if we have 0.2 moles of a non-volatile solute dissolved in benzene? What's that going to do to the boiling point of that benzene? Well, here's the deal. We know, because we've just said it, that it's going to increase the boiling point. And why is this? Because note, pure benzene at 80 degrees Celsius would be boiling. However, if you have 0.2 moles of a solute, we now know that through Raoults law that the normal pressure of benzene, if it was at 80 degrees Celsius, the normal pressure of benzene would be 760 millimeters of mercury. However, the mole fraction was 0.865, which means the pressure that would be inside one of these bubbles trying to form would only be 657 millimeters of mercury. Because we put that solute in there, that non-volatile solute, the vapor pressure of the solvent went down. In order to get this to boil, though, in order to get benzene to boil, the vapor pressure inside a bubble of benzene has to be 760 millimeters of mercury, because that's our outside pressure. That's the pressure of the rest of the benzene, is 760 millimeters of mercury. Normally, review it again, normally for pure benzene, you can get 760 millimeters of mercury pressure inside the bubble equal the outside pressure at 80 degrees Celsius. But now that it is mixed with this 0.2 moles of a non-volatile solute, the pressure inside a bubble at 80 degrees Celsius would be 657 millimeters of mercury. So if the pressure inside that bubble, they cannot form because it's too low, it's only 657 millimeters of mercury, what do we need to do to raise the pressure up to 760 to get the pressure of the vapor pressure of the benzene gas equal to the external 760 millimeters mercury? We need to add heat, which means the temperature is going to increase because it's not boiling. So you need to increase the temperature to boil the solution to get the pressure of the benzene back to 760 millimeters of mercury. And now you're probably saying, boy, that's fun. Wouldn't it be nice if there was some equation that we could memorize that discusses this? You're in luck. Here we go. Yeah. So here we have our boiling point elevation equation. The boiling point elevation, the change in the temperature of the boiling point, the number of degrees at the boiling point increases, equals kBp, the mole boiling point elevation constant. You have to look that up in a book. Is degrees Celsius per molal times the molality of the solute. Note, it's not the molarity, it's the molality. The moles of solute per kilograms of solvent. All right, so let's look at an example calculation here. What is the boiling point of a solution of 0.144 grams of eugenol, C10H12O2, dissolved in 10 grams of benzene? Note, we've got much less eugenol, 0.144 grams of eugenol, much more benzene, 10 grams, so benzene is our solvent. So the question is, what's going to be the new boiling point of this mixture when we put the eugenol in the benzene? Recall, pure benzene boils about 80 degrees Celsius. What's the new boiling point? Well, we just need all of our factors for this equation. This is what we're after. Our change in boiling point is what we're after. We need this constant, and we need the molality of the solute. All right. So, well, change of boiling point. The molality of the solute, well, we know we've got 0.144 grams of eugenol. Here's its formula, so we now can calculate the molar mass. Grams divided by molar mass gives us 8.77 times 10 to the minus fourth moles of eugenol. Recall the molality then is the moles of eugenol divided by the kilograms of solvent. Therefore, the molality of our eugenol is our 8.77 times 10 to the minus fourth moles of eugenol divided by 0.010 kilograms of benzene. We had 10 grams of benzene. That's 0.01 kilograms of benzene, which means we have 8.77 times 10 to the negative second molal eugenol. Now, looking up at the constant for benzene, we find the constant for benzene is 2.53 degrees Celsius per molal. This is from benzene from a table. So now it's just plugging in this number and this number into this equation up here. Okay. Our change in boiling point is going to equal 2.53 times 0.0877, which gives us 0.222 degrees Celsius. Note, that's boiling point elevation. So if our normal boiling point of benzene is 80.10 degrees Celsius, something else we get from a table, we know our change in boiling point is 0.222 degrees Celsius. Since it's boiling point elevation, we add the 0.222 to the 80.1, and we get 80.32 degrees Celsius. Something to note, that is not a drastic increase in the boiling point. Yeah, note, we had 10 grams of benzene. We had 10 grams of benzene. We added 0.144 grams of eugenol, and the boiling point went up from 80 degrees Celsius, or 80.1 degrees Celsius, to 80.32 degrees Celsius. So when we're talking about these boiling point elevations, it's not a drastic, huge change in boiling point elevation. Okay? Which means if you're boiling water on your stove, pure water, and say it's at 100 degrees Celsius, if you add some salt to your water, just shaking a couple of shakes of salt into your pasta water, you're really not increasing the boiling point by very much. You're adding so little salt to it, and the boiling point just doesn't change that much by adding salt to it. A little bit, but not much if you're just salting your pasta water. All right. We'll cover this next one quickly because it's pretty much the same. Boiling point elevation, another colligative property is freezing point depression. Just as increasing the number of solute particles increases the boiling point, increasing the number of solute particles decreases the freezing point. A solution will freeze at a lower temperature than the pure solvent. And this is why you put stuff on the sidewalks, salt solutions on the sidewalks, when it's cold out to melt the ice. Because ice, which is water, freezes at 0 degrees Celsius, but if you put salt on that ice, that will lower the freezing point, and if you can lower the freezing point of the ice to below the air temperature, then the water won't freeze and you can walk on your sidewalk without slipping and breaking your tailbone. All right. The equation for freezing point depression is the same as the equation for boiling point elevation, except it's freezing points. The change in freezing point equals a constant, a freezing point constant, times the molality of the solute. But the calculations are going to be the same. The freezing point depression constant is from a book. You have to find the molality of solute, and you can find the change in freezing point. Nope, you have to subtract the value, the absolute value of the change in freezing point from the accepted freezing point of the pure solvent because it's freezing point in depression. But the take-home message with these two properties is if you add a non-volatile solute to a solution or to a solvent, the boiling point of the solvent increases, the freezing point of the solvent decreases. All right, this video's getting a little long. We will continue with osmosis and colloids in the next video.